Hello everyone. So I want to talk about the continuity equation. The continuity equation contains the physical idea that mass is conserved in some flow. The rate of mass going into one end of a pipe or through some surface is equal to the rate of the mass coming out of some pipe or out of some surface. Essentially, it's the idea of what goes in must come out. In order to get at the mathematical expression, let's take a look at this situation. I've drawn a pipe here, and we can imagine some fluid coming in this side at some velocity. And I've drawn some surface here. I've drawn this black surface that has some area A. And what I'm interested in is the rate at which mass goes through this surface. What is the rate of mass, the amount of mass per unit time that passes through A? So that's the question we're trying to ask. So let's think about this fluid flowing for a bit. If we leave the fluid to flow, so what happens? Every little dot of fluid that is on this surface in some time will flow this way. Right? It'll flow down this way. And because we're making this assumption of laminar fluids and no viscosity, all of these will flow to some point on some other little cylinder here. So it's done this in some time, delta t, and it's spanned some space in that time delta t, delta x. Well, let's take a look at what we're trying to solve here. We're trying to solve for delta m divided by delta t, which we know we can write as some density of the fluid times some volume over delta t. Well, what is this volume? We see that the fluid that is flown through this surface A in some time delta t is actually the volume of this cylinder, right? That's the amount of water in delta t that is flowed through surface A. Well, we can use the variables that we have to represent this volume in a different way. We have rho. Well, what's the volume? The volume is delta x times A. Right? That's the volume of that little cylinder of fluid divided by some time delta t. Well, if we recognize that dx divided by dt is the velocity, then we find that this is simply rho A times v, the fluid flow of the rate of fluid flow of the volume we had. So we have this first expression. This first expression is called the mass flow rate. Okay, we're going to use this idea of mass flow rate to now derive the continuity equation. One of the ideas that we have a sense for is that if we have some amount of mass per unit time coming into one side of the tube, then the same amount of mass must be coming out per unit time out of the other side of the tube, right? If this weren't true, it would mean that mass were lost or gained somewhere in the middle of the tube, and this isn't true. This is basically the idea of what goes in must come out. And we can set up an equation that relates these two things. Using our idea of fluid flow, we can rewrite this equation in terms of different variables. We know that if this has area 1, and this has area 2, and the fluid is coming in through this surface at some velocity 1, and the fluid is coming out of this surface at some velocity 2, and the fluid has some density, rho 1, coming into here, and some density, rho 2, coming out of this side, then what this equation says is that rho 1 v1 a1 is equal to the density at point 2 times the velocity of fluid coming out at point 2 times the surface area of point 2. So this here is known as the continuity equation, and it's an application of the idea of flow rate. That's a funny looking box, but I'm going to keep it. It's the application of the idea of flow rate. A big assumption we'll make in this course is that fluids are incompressible. Gases are generally compressible. So this would hold for gases, but a lot of the fluids we're going to deal with, liquids, are incompressible. So for incompressible fluids, rho 1 is equal to rho 2. And our expression simplifies. And this is an equation you're going to see a lot of as well.